Good morning, everyone. Today we have started discussions of the applications of Wheatstone bridge. The first application is the meter bridge. Can you see the diagrams in the left hand corner of the boards? This is the constructions and diagrammatical representations of the meter bridge. Okay, let's start discussions of the meter bridge, how it can be constructed, and what is the functions and principle of the Wheatstone bridge. This meter bridge is working on the principle of the Wheatstone bridge with the help of some balancing conditions. What is the balancing condition? That means they are under the ratios of their resistance, equiratio of their resistance, or these are parallel connection of the resistance. Consider this is the unknown resistance X and this is the known resistance R. We can calculate the unknown resistance with the help of known resistance using the meter scale. Then why we call the meter bridge? Because they have a 1 meter long uniform wires. That is the construction of meter bridge. We have 1 meter long uniform wire that take 1 meter long uniform wire on the meter scale on the meter scale. This is the meter scale. A to B is the 1 meter wires and A to B. Connect the potential across the two ends of the conductor or two end of 1 meter wires, that is AB. Connect potential across AB. That means A have the higher potentials and B have the lower potentials. And two L-shaped, these are the two L-shaped rod plates. Two L-shaped conducting plates or rod. Two L-shaped conducting plate or rod, conducting plates which are connected both points or both end of the meter scale, which are connected, conducting plates connected both ends of meter both ends of meter scale, or that is A and B. We are connected one conducting rod in between two L-shaped plates, connected one in between two L-shaped rods or two L-shaped conducting plates placed a conducting rod. First, can take a uniform 1 meter wires along the meter scale. This is the meter scales which having such digits, centimeter, 1 centimeter, 2 centimeter up to the 100 centimeters from A to B, and take the uniform conducting wire placed in between the A to B. These are the 1 meter wires, and the potential difference are connected across the two ends of the meter bridge, that is A and B, across the 1 meter scale. And we connect the rheostat to calculate or to change or vary the resistance. And two L-shaped conducting plates are connected to either sides of the A and B, two ends of the meter scale. Then in between these two L-shaped conducting plates, we kept one of the rod to connect these two ends. And the the galvanometer is placed. The galvanometer is placed from point C to, this is the point C to the moving key. This D is a moving key, that is also known as to the moving key called jockey. Moving key called jockey. When the galvanometer is shows deflections, the current is passes through the A to B or B to A, any other conditions. When the galvanometers are kept, consider this is the galvanometers and the needle of the galvanometer is in the direction of left. We can continuously sliding the jockey on the meter scale. Then on these meter scales, not the only meter scale, they have one wires on a meter scales. At such points, the galvanometers are perpendicularly steady in a vertically steady. That means they has a null points. Jockey get a null points. At that times, the jockey are vertical placed or the needle in the galvanometer is straight, upward straight. That means these are the null points. And the resistance in the wire, the resistance in that wire between the A to D is R of AD, and the resistance in the wire between the B to D is the resistance of BD. Okay, this is all about the constructing part, and now we're dealing with the working, how it is work. Working is most important thing because the working of meter scale is working on the principle of Wheatstone bridge. Meter bridge is on the principle of Wheatstone bridge. The most important and special conditions of the Wheatstone bridge, they are following: equal ratio of parallel, equal ratio of parallel resistance. We know that the resistance R of AD and R of BD are the resistance, are the resistance between points, are the resistance between the points A to D and B to D in the meter wire, in a meter wire respectively, in the meter wire respectively. The resistance in between the A to D in that wire is R of AD. The resistance in between the B to D in that wire are a BD. Now we know that the balancing conditions of the Wheatstone bridge, the balancing condition of bridge, that is balancing condition or the special condition, that is X upon R. X upon R. These are the, and X is unknown resistance, R is a known resistance, which are kept in between the C to the left hand side rod. Is must be equal to R of AD and R of BD. Now L1 and small l2, small l1 and small l2 are the length of the wire, or length between, that is L1 is the A to D, this is the length L1, and L2 is the remaining one length, that is B to D. Length between AD and BD respectively. AD and BD respectively. If we know the L1, these are the meter scale, calculate both L1 and L2. But if we know the L1, must be calculate the L2. That is L2 equal to 100 minus L1 in centimeter. Because the total length in between the A and B is 1 meter. A, D, B are the collinear points. That means AD plus BD equal to AB. Then we know that AD. Then calculate AB minus BD. Then we know that the resistivity is directly proportional. Resistivity is directly proportional to the length and inversely proportional to the cross-sectional area. Resistivity depends on the length of conductor and cross-sectional area of that conductor. But what happens are resistivity equal to R into L upon A. We know that R equal to resistivity into L upon A. That is, the resistance of that particular conductor is equal to resistivity into length upon area. Now, for the AD, for resistance AD, R of AD is equal to distance R of AD is equal to rho into L1 upon area. Cross section, because these are the uniform wire. That means the cross section area is similar at every places. Then what happens R of BD? R of BD is equal to resistivity. The length is L2 upon A. And this is the equation number one or spatial equations for the spatial condition. Okay, the value of R of AD and R of BD we can given from here kept in the equation number 1. Put the value of R of AD and R of BD in the equation number 1. What happens? We know that x upon R is equal to value of R of AD, that is rho into L1 upon A, rho into L1 upon A divided by rho upon L2, rho into L2 upon A, that is rho into L2 upon A. The similar term which are present in the numerator and denominator, they get cancelled to each other. That means rho are cancelled and area, cross-sectional area are must be cancelled because the wire has the same material. That means resistivity of the material is same and the wire is same. Wire is uniform. That means the cross-sectional area of that wire is must be same at every places. We know that the new equation, that is x upon r equal to L1 upon L2. We must be calculate the unknown resistance x with the help of known resistance and these are the length. That means x is equal to L1 upon L2 into R. This is the final equation to calculate the unknown resistance with the help of known resistance and the null points. Just revise the process, how it can work. When we see the diagrammatical representation, then we write the constructions of that meter bridge. But what is the working? In the working, we know that R of AD and R of BD, R of AD and R of BD are the resistance of that uniform wire in between the A to D and B to D. The length of that wires in between the A to D say L1 and the length of wire in between the B to D say L2. Now, points and meter bridge. The balancing condition in the Wheatstone bridge. The balancing condition of the Wheatstone bridge is equal to x upon r. These are the parallel to each other. X upon r is equal to r of AD upon r of BD. This must be equal to resistance of the uniform wire in between A to D and resistance of the wire in between B to D. Then we know that the resistivity is depends on the length, cross-sectional area, and the resistance of the wire. The resistivity is depends on the length of wire, cross-sectional area of the wire, and resistance. We know that R equal to rho into L upon A. That is resistance equal to resistivity into length into the A. For for R of AD, the resistance of that wire in between A to pointer D is must be equal to the resistivity of that wires into the length between A to D is L1 and cross-sectional area. The wire is uniform. That means the cross-sectional area is similar at every places. That means A does not changes for R of AD and R of BD. But the length will be changes. That is L1 and L2. Now, the R of AD is equal to rho L1 upon A and R of BD is equal to rho L2 upon A. We know the equation number 1 for the balancing condition of Wheatstone bridge. The kept value of R of AD and R of BD from these equations at the equation number 1. And we get x upon R, this is the left hand side, R of AD is must be equal to rho L1 upon A, and R of BD is must be equal to rho L2 upon A. Kept in that value. The similar term which are present in numerator and denominator gets cancelled to each other. Then we know that x upon r equal to L1 upon L2. Then x is equal to L1 upon L2 into R. These null points having the equipotential between the L1 and L2. The potential difference between the AD and BD are same. This is the most important concept to calculate the unknown resistance with the help of known resistance. This concept is a meter bridge. It will be asked 2 to 3 marks in the 3 to 4 marks in the descriptive examination, but a lot of questions will be asking on that concept in MCQ. Thank you.